Math 265A, Quest to College. I'm Joe Vasta, and we are going to cover 4.7. This is called L'Hopital's rule. L'Hopital was a person, so you would say his name L'Hopital. Yeah, he never got teased in school. Anyway, so let's go ahead and look at L'Hopital's rule, which we're not going to prove this theorem. It has everything to do with limits. And so you're going to feel like you are back in the stage of calculus where you were cranking out limits. And in your homework, you're going to get a lot of limits to crank out. The theorem says that if you go to take a limit, you have f of x over g of x. And you end up getting 0 over 0, or infinity over infinity, or negative infinity over infinity, or infinity over negative infinity. So basically we'll just say 0 over 0, infinity over infinity. Then you can crank out the limit by taking the limit of the derivative of f divided by the derivative of g. And these things, 0 over 0, infinity over infinity, etc., those are called indeterminate forms, which means one function might have 0 over 0 and the limit might be 0. Another function might have 0 over 0, the limit might be 7. So they're indeterminate because you can't determine just from that what those will become. Let's go ahead and do some problems. The rest of this section will be me working out some problems, and really just, I'm doing derivatives. So what do we have here? We have, whenever we get a limit, we like to plug the number into x to see what we would get. On the top we get 4 minus 4, which is 0. On the bottom we get 0. So this thing goes to 0 over 0. So this is a great problem to do L'Hopital's rule on. When I do L'Hopital's rule, I'm going to go put an H there, which means, that's part of his name. And L'Hopital's rule says we're going to go ahead and take this limit, and we do the derivative of the top, which is 2x, and the derivative of the bottom, which is 1. Now notice what we did. We did L'Hopital's rule. We did not do the quotient rule. I'm not taking the derivative of that function. I'm saying the derivative of the top and the derivative of the bottom, and then doing the limit. When I go ahead and put the limit in there, I end up getting 2 times 2 over 1, which is 4. So that is how you apply L'Hopital's rule. They're going to ask you to use it when it's convenient and applicable. So when it's applicable, we want to use it in these problems in our homework. Also note that if you're getting ready for the test, the work is important. Every step you write. Instead, I don't want to just see, oh, the limit of this is 4. Okay, you might also look at this graph and remember that the top can be factored into x plus 2, x minus 2. The x minus 2's cancel. This is really a line with a hole in it, and the hole happens to be right at this trouble point, and so the limit still does exist. So you could actually look at that graph if you'd like, but we are doing the limits using L'Hopital's rule. Let's go ahead and do the next problem here. Problem number 2. Okay, so we have limit as x approaches 1, ln x over x minus 1. Now, you might have remembered that the ln of 1 happens to be 0. There's 2 ways of getting it. One way you're not going to like is remembering that the ln graph goes like that. And so this is y equals ln x. And you can see that if you're at x equals 1, the y value is 0. Another way is to say log base e of log, so you're going ln 1. So you could actually say, oh, e to what power gives you 1, e to the 0. In any case, or you can use your calculator. You end up getting 0 over 0. So this is a time to use L'Hopital's rule. L'Hopital's rule says we take the derivative of the top, which is 1 over x, and then we put it over the derivative of the bottom, which is 1. Okay? So this gives me, I'll just simplify that expression there. The limit as x approaches 1 of 1 over x. Now I don't want you to get the wrong idea. This is just the graph of y equals ln x. It's not the graph of the thing we're trying to find the limit of. So now I put 1 in for x, and that works out. I get 1 over 1. So my answer is 1. So I believe you've done worse things in a math class. This is not one of the worst things you've done. Maybe a little boring, I don't know. Let's go ahead and do problem number 3. Maybe you can do problem 3 on your own by pausing the video and seeing if you can get an answer to this. Okay, so this is a very famous limit problem in calculus. The limit as x approaches 0 of sine x over x. Sine of 0 is 0, and then put 0 in the bottom, that's 0, so this guy goes to 0 over 0, which is another good candidate for L'Hopital. So L'Hopital's rule says we take the limit as x approaches 0. We take the derivative of the top, which is the cosine of x, and the derivative of the bottom, which is just a 1. Okay, now I'm going to go ahead and put 0 in for x, and we know that the cosine of 0 happens to be 1, so we have 1 over 1, which is 1. So before we had L'Hopital's rule, we could do some crazy things with this and try to figure out what the limit is. You know, we do have squeeze theorem, we have some other things that we've done in the past. But now with L'Hopital, we have a lot of power here. So we got our answer of 1. Let's go move on to the next problem here. This is basically all you do in your homework. You just take in some limits. The limit as x approaches 3 of this expression here. So let us go ahead and see what happens when you put 3 in. You get 0 on the top, and you get 2 on the bottom. 0 on the top and 2 on the bottom. So what is this going to give me? Well, I'm going to say this equals. Did I say 2 on the bottom? Okay, no wonder. I don't know. I was thinking of an unrelated thing. Sorry about that. Should pause the video and edit it and all that stuff, but I'm not going to do that. I get 0 on the top, and I get 5 on the bottom. You're like, well, what was the unrelated thing you were thinking about? Not going to tell you. Okay, so what is 0 over 5? Well, 0 over 5 happens to be 0. So this just goes to show you that not everything is L'Hopital's rule. In fact, I mean, you don't have to write this, but there is no, whoops, there's the L, L'Hopital. No L'Hopital rule. Okay, so you don't, that's not part of the answer. Now, you might be taking calculus somewhere else or seeing calculus in other places. There is an alternative spelling that they'll use in the book, and not in our book, but in other calculus books, and it will look like this. So it will be like that. So it looks like hospital, and some of you might be thinking, that's where I need to go if I keep taking math classes. So 0 is our answer. there was no L'Hopital's rule. We just kind of threw that in there as a, I don't know, a special treat. Don't you hate when teachers say things like that? Okay, let's go ahead and take the derivative of this guy right here. In all of our problems we've been doing, we've been getting 0 over 0. We have not gotten an infinity over an infinity. And we wanted you to get used to L'Hopital's rule before we did some infinities on the top and bottom. So I have limit as x approaches 0 of this creature here. Let's go ahead and put 0 in. When we put 0 in, we get 1, because e to the 0 is 1, minus 0, minus 1. And on the bottom, we get 0 squared. So we end up having, this is 0 over 0. Okay, we don't want to say that it equals 0 over 0. And so this is a good time to do L'Hopital's rule. L'Hopital's rule, and maybe you want to finish these problems, you know, maybe at the beginning of each problem you want to pause the video and see if you can do these yourself. So we have limit as x approaches 0. Derivative of the top, e to the x minus 1 plus 0. On the bottom, we have 2x. So there it is. Let's go ahead and put 0 in. We get e to the 0. So we get 1 minus 1 on the top and 0 on the bottom. So this gives us 0 over 0. Wow, so what do you think we have to do? What we have to do is apply L'Hopital's rule a second time in this problem. And so, when we apply it a second time in this problem, the derivative of the top is now just e to the x. The derivative of the bottom is 2. We go ahead and put 0 in. We get 1 on the top, 2's on the bottom. So our answer is 1/2. So sometimes you have to apply L'Hopital's rule 2 times. Sometimes you might even have to apply L'Hopital more than 2 times. And just do all your homework and you'll see. Okay, let's go ahead and do another problem. There's a star up there, and I'll tell you why the star is up there, but for now let's just go ahead and do this problem. So we put 0 in and we get e to the 0, so that's 1 minus 1. That's 0 on the top and 0 on the bottom. So I'm going to apply L'Hopital's rule. This is going to give me the limit as x approaches 0. The derivative of the top is a little chain rule there. So 2e to the 2x. The derivative of the bottom is 5x to the 4th. So now on the top, when you put 0 in, you end up getting just a 2. On the bottom, when you put 0 in, you end up getting 0. Okay, so now here's the deal, and you might want to think back to the other limit sections earlier in this calculus class. This 0, as you're approaching 0 from both sides, it's an x to the 4th. It's going to be a very small, tiny positive number, and so remember I had the notation that looked like that. Now, when I have 2 over a very small positive number, hopefully you'll remember what the limit is. The limit happens to be infinity. And so that is the answer. So why is there a star here? Well, there are problems like this in a typical calculus book. Our calculus book does not have, I believe it does not have any problems in the section where the answer is going to be infinity or negative infinity. But I put this in here just to show you a problem like this in case it happens later on in another technical class you're taking. Okay, so let's move on to number 7. I'm going to do one that has some trig in it. So this has a little trig in it. And we have the limit as x approaches pi halves of x minus pi halves over the cosine pi halves. Now if you remember the cosine graph, it looks like this. So these are graphs worth remembering. It does a full cycle into pi. Here's pi, and here is pi halves. So this is y equals the cosine of x. And so that usually jogs people's memories in terms of what the cosine of pi halves is. That's 0, and we have 0 on the top. So this thing goes to 0 over 0, which means it's a time to do L'Hopital's rule. L'Hopital's rule says the limit as x approaches pi halves, and the derivative of the top, well, is just going to be 1. The derivative of the bottom is going to be negative sine. Okay, so now I'm plugging pi halves into sine of pi halves. Now, sine looks like this. So here is 2 pi, here is pi, right here is pi halves. And I didn't draw this on the other graph, but the amplitude of these regular graphs happen to be 1. So the sine of pi halves is 1. You have that negative in front of there, so we're going to have 1 over negative 1, which is negative 1. So I wanted to do one that had trig in it. We'll do some other ones that have trig in it as well. So let's go ahead and do some other things, and we'll still see infinity over infinity. Just want you to feel comfortable with this. Maybe I'm doing too many problems, but it's good to see lots of problems. Number 8. So we have x approaches 0. This is a limit, so we have sine of 0, which is 0 minus 0. So we have 0 on the top, 0 on the bottom. Let's go ahead and apply L'Hopital's rule. So L'Hopital's rule says the limit as x approaches 0, we take the derivative of the top. The derivative of sine is the cosine. The derivative of x is 1, so I'm going to go minus 1. This is all over 21x squared. Now, I suppose I forgot to do this, which is a good thing to do to show everybody, hey, we've just figured that out. Let's go ahead and put 0 in here. The cosine of 0 is 1. So this is 1 minus 1 on the top, 0 on the bottom. So this is 0 over 0, which means it's time to go to the hospital again. L'Hopital again. We have limit as x approaches 0. We're going to take the derivative of the top. The derivative of the cosine is negative sine. The derivative of a constant is 0. And the bottom, we're going to end up getting a 42x. I go put 0 in here. The sine of 0 is 0. The bottom is 0. It looks like we have 0 over 0. It almost seems like we are in an infinite loop. I'm going to do L'Hopital's rule again. The derivative of the top happens to be, the derivative of sine is cosine, so this is going to be negative cosine on the top because of that negative sign. And on the bottom we have 42. I'll go ahead and put 0 in for x on the top. Cosine of 0 is 1. We have negative 1 on the top and 42 on the bottom. So here's a problem where we applied L'Hopital's rule 3 times on a complicated function, and we ended up getting the limit. Okay, let's go ahead and continue doing some of these problems. We are going to do problem number 9, where now we have the limit as x approaches infinity. And notice what we have on this one. On the top, we have 2 times infinity squared plus 3 times infinity plus 1. That's going to infinity. And the bottom we have 5 minus 7 times infinity squared. That's going to negative infinity. Why? Because you have that negative there. But in any case, even if it was going to positive infinity on the bottom and positive infinity on the top, this is a time when we have to do L'Hopital's rule. So L'Hopital's rule says we take the derivative of the top, which happens to be 4x plus 3, and the derivative of the bottom, which is going to be negative 14x. Okay, so I go ahead and put infinity in again, and I end up getting infinity on the top, because 4 times infinity is infinity. Infinity plus 3 is infinity, so there's the infinity on the top, and negative 14 times infinity is negative infinity. Time to apply L'Hopital's rule a second time on this problem. So the derivative of the top is 4. The derivative of the bottom is negative 14. And now we don't have any more x's, so we've taken the limit of just a constant is just going to be that constant, which is negative 4/14, which actually equals negative 2/7. Now let's say a few things about this problem. We are finished. But this is a polynomial over a polynomial, which is a rational function, and you would have learned something in pre-calculus about the horizontal asymptotes, which is really what happens when x gets toward infinity and negative infinity. And you were told to find them on a problem like this by looking at the degree on the top and the degree on the bottom, and if they were the same, you went ahead and went with the coefficients. And you were just told that. Well, that's the rule you memorize. Well, this, we can do a more general example, but this is the rationale behind that rule and some of those other rules you've learned in your homework and on the test. When you're given a problem like this, we want you to show L'Hopital's rule and the work to get here. So that is the deal. So when you're doing these problems on the test, make sure you write this all down, because I think the problems did say, you know, when appropriate, use L'Hopital's rule. Let's go ahead and do another problem, which is the limit as x approaches infinity, ln x over the square root of x. Oh, by the way, you know, on this problem there is another way of doing this problem, and we did these problems earlier. We can multiply top and bottom by 1 over x squared. So when you do that, you get 2 plus 3 over x plus 1 over x squared, and then 5 over x squared minus 7, and then send x toward infinity. You'd end up getting the same answer, which is right here. But the deal is, in this section, use L'Hopital whenever you can use L'Hopital. So on this one, we have the ln of infinity. Now remember, the ln looks like this. And so if you are approaching infinity, and you're putting that into ln x, so y equals ln x, the y is going to go to infinity. This is all over the square root graph. Y equals the square root of x looks like this, half parabola. It also goes to infinity. They almost look the same, but they're not. Okay, so this is y equals the square root of x. So what's happening here is we are going to infinity over infinity. So this is, so we did say we would do infinity over infinity, and the last one was one of those, and so is this one. So it's time for L'Hopital's rule. So L'Hopital's rule, we are going to take the limit as x approaches infinity. The derivative of the top is 1 over x. The derivative of the bottom, okay, so remember the bottom looks like this. I'll do this off to the side. So its derivative is 1/2 x to the negative 1/2. Or we can write this as 1 over 2 root x. Okay, so that's what we're going to write. 1 over 2 root x. Okay, so what do we have here? We have the limit as x approaches infinity. I'm going to do a copy dot flip, copy dot flip. And so, I mean, if I had written that as the 1/2 power, I would end up canceling that and getting something like 2 over the square root of x, or rationalize the numerator, but that is what we're getting. So maybe it would have been best if I had just kept that as the 1/2 power, and then this is the 1 power, and you would have been able to cancel a little or subtract. Okay, now when I put infinity into this, I end up getting 2 over the square root of infinity. I mean, that thing's still going to be infinity. And when you have 2 over infinity, what does that give you? That gives you 0. Okay, so the limit of this guy is 0. So notice, you know, when you had an infinity over here, it gave you a negative 2/7. You have an infinity over infinity here, it gives you a 0. That's why these things are called indeterminate forms, because we can't determine what it's going to give us just by seeing an infinity over infinity. So let's give you a list of a few more indeterminate forms, and we'll see how that plays out. So we have, these guys are L'Hopital, and you know, we could put negative infinity over infinity, etc. That's what we've been doing. Mostly these ones. But these ones, you know, these are the ones where you can do L'Hopitals. Now when you have 0 times infinity, because, you know, we've seen that 0 times like numbers equals 0, and infinity times most real numbers except 0 will give you infinity. But when you have these guys battle it out, they're indeterminate. And same with infinity minus infinity. And you might think that's 0, but it's not going to be 0 all the time. So those are 2 more indeterminate forms, and you will use algebra or some trig to turn into something that you can do L'Hopital on. These guys right here are the bad boys, okay? And we'll do examples of this. This is where you have 0 to the 0, infinity to the 0, 1 to the infinity, and we're going to use natural logs, whatever that means. And I mean, you can look at this, you could say, oh, I remember 0 to any power is 0. And then you might say, I remember a number to the 0 power is 1. But if these guys had a battle, they are indeterminate, and we'll show you how to do this. Same with these guys here. So let's go ahead and do a few more problems, and then we'll be done with section 4.4. So the limit as x approaches pi halves from the left. So remember that that's what that means. And the function is secant x sine 2x. So how are we going to do that? So well, let's put pi halves in, and wow, secant. So if you remember the graph of secant, and some of you might not, it rests on top of the cosine, because let's see, the secant equals 1 over the cosine, so the cosine looks like this. And so here's pi halves. And the secant, you know, 1 over, you know, here's 1, so 1 over 1, and everywhere there is an x-intercept on the cosine, that gives you a vertical asymptote on the secant. So the secant looks like this, it looks like that, and then it looks like this. So good thing we said we are approaching pi halves from the left. So on this black graph, we are going to where? We're going to infinity, not negative infinity, because we're approaching this from the left. So this is going to give us a negative infinity. Oh, sorry. Did I say? This is going to give us an infinity. And then sine of pi halves sine of 2 times pi halves, I'm sorry. So here is, I'm just going to go ahead and draw the sine graph. This is just the regular y equals sine x. I know we don't have that there, so maybe I shouldn't have drawn it. But look, I'm going to go 2 times pi halves. When I go 2 times pi halves, the 2's cancel, and I'm just doing sine of pi. Sine of pi is 0. So this is an infinity times 0, which was one that we had on our indeterminate form. Now some of you might go, no, we had 0 times infinity, same thing. So how am I going to do this? I cannot go ahead and apply L'Hopital's rule, but what I'm going to do is I'm going to write the secant as 1 over cosine. See what that does. So pi halves from the left, And then we have, this is really going to be the sine 2x over the cosine x. Let's see where this goes to. Well, we know that sine 2 times pi over 2, that's going to be the sine of pi, is 0. And we know, we'll draw another graph here. So this right here is pi halves. This right here is pi, and then, you know, oh yeah, this right here is 3 pi over 2. We know that the cosine of pi halves is 0, so look what we have here. We now kind of just manipulated this with the trig identity and got 0 over 0. So that was not a L'Hopital, that was just doing some trig. Let's apply L'Hopital's rule. L'Hopital's rule says the limit as x approaches pi halves from the left, and we're going to take the derivative of the top, which is a little bit of a chain rule. The derivative of sine is the cosine, and then the derivative of that something, you know, the 2x is a 2. And on the bottom, we take the derivative of the cosine, which is the negative sine. Okay, so we put pi over 2 in here. We get 2 cosine of 2 times pi over 2, which is going to be pi. And then this is negative sine pi over 2. We don't have to say from the left because these guys do not have any vertical asymptotes. So look what we have here. We have 2 times cosine of pi. Cosine of pi is negative 1. I'm getting that from the picture. And the sine of pi halves, which is right here, is positive 1, but there's a negative in front of there. So I get negative 2 over negative 1, which is a positive 2. And at any time you can put this function, secant x, sine x, into Desmos or one of the graphing programs and see what the picture looks like, and you'll see that the limit, looking at the picture, will approach, the altitude will approach 2 from both sides. Oh no, from the left side on this. Okay. But they don't ask you to do that in the homework. Let's go ahead and do a few more problems. We have the limit as x approaches 0 from the right, 1 over sine x minus 1 over x. Okay, so what do we have here? 1 over 0. 1 over 0 from the right. Okay, so, you know, once again, this is, the sign looks like this. You're approaching 0 from the right, so this is 1 over 0 with a plus by it, so that first one's going to be infinity. And then 1 over x looks like this. And we don't really need to use the graph. You can say 1 over a very small positive number. That's going to be minus infinity. Okay, so this is going to be a problem. Now, if this had said a plus and we got infinity plus infinity, we'd be done. We'd say the answer is infinity. But this one, we've got to be careful here. So what am I going to do to fix this? This is our infinity over infinity, which was on our list. We cannot just do L'Hopital on this. What I want to do on this, so let's go ahead and just take a look at this. Well, what I want to do is get a common denominator. So it would be x sine x. So this would give me the function x minus sine x on the top, and on the bottom I'd have x sine x. And now we're still doing the limit as x approaches 0 from the right of this guy right here. Okay, so we go from here down to here. Let's put 0 in, and on the top we get 0 minus sine of 0 is 0. And on the bottom we get 0 times sine of 0 is 0, we get 0. So by doing a little algebra and putting that into one fraction, we get 0 over 0. We took this infinity minus infinity and turned it into that, and now it's time to apply L'Hopital's rule. L'Hopital's rule says we're going to write this limit down, and we're going to take the derivative of the top, which happens to be 1 minus cosine x. All over. Now on the bottom we have the product rule, because we're just taking the derivative of the bottom. So the derivative of the first, which is 1 times the second, plus the first times the derivative of sine, the second, which would be that. Okay, now I'm going to go ahead and maybe I'll use another piece of paper on this one. So let's just rewrite it nicely. So it says the limit, well, I guess I could have just plugged 0 into that. 1 minus cosine x, and on the bottom I have sine x plus x cosine x. Okay, so I put 0 in on the top. The cosine of 0 is 1, so I have 1 minus 1, which is 0, and on the bottom I have sine of 0 is 0, and then I have a 0 here times a 1, so I have 0 on the bottom. So, wow, I've got to do L'Hopital's rule a second time on this problem. But I can do that because it's 0 over 0, so I can get away with it. And so the derivative of the top is, derivative of a constant is 0, derivative of negative cosine is going to be, well, the derivative of cosine is negative sine, so this is actually just going to be the sine x on the top. And on the bottom, we have the cosine of x, which is that derivative, and then a product rule here, which is the derivative of the first, so I'm doing this term right here, which is 1 times the second, which is cosine x, plus the first, which is x, times the derivative of the second, which is negative sine x. So I'm going to go minus x sine x. So what do I have when I put 0 into this again? I get 0 on the top, and then I get 1, because cosine of 0 is 1. 1 plus 1. 1 plus 1 minus 0. So this gives me 0 over 2. And 0 over 2 is defined, it is defined to be 0. And so on these problems here, the problem started off with an infinity minus infinity. We just did a little algebra and got a 0 over 0 when we hit it with the limit. And we got our answer of 0 for that one. Okay, so we have 2 more problems in this section. This one right here, number 13. Is one of the bad boys. That's where we have something to a power. Let's see what we get when we put 0 into this. We put 0 into this, we are going to get 0 raised to the 0. Now it doesn't matter whether we're coming from the right or whatever when I'm plugging it in there, so this is a bad boy. So what am I going to do with this? I'm going to do this very carefully. I'm going to say that y equals the thing that I'm going to take the limit of. Okay, now I'm going to ln, take a natural log on both sides of that. So ln y equals the ln of x to the 4x. And then what I'm going to do is I'm going to say that this 4x in the exponent, using the power rule of logs, can jump down in front, so it looks like 4x, and then we have times the ln of x. Okay, so what I want to do on this is I'm thinking about taking the limit as x approaches 0. Okay, so that's what I want to do. I want to take the limit of this as x approaches 0. So let's show you this. So I'll take the limit as x approaches 0 of ln y equals the limit as x approaches 0 of this right here, which is 4x ln x. Now, when I put 0 in, I end up getting 0 times ln of 0, and I'm actually coming from the right, so good thing they wrote the problem this way. Remember, the ln graph looks like this, so as I'm approaching 0 from the right, this is going to negative infinity. So this is kind of weird. This is a 0 times an infinity, or a 0 times a negative infinity, so I have to do some trick to this to make it so it can be something that we can do L'Hopital on. So the trick that I'm going to do is I'm going to take this x. Okay, so watch this. I'll leave the 4 up here. I'm going to take the x and I'm going to write it as 1 over x on the bottom. Now that is pretty tricky. It's something you probably wouldn't have thought of doing, but look at this. If you go copy dot flip, you can copy the top, dot, and then flip that, you'll end up getting this thing right here. So I'm taking the limit of that. Now when I do that, 1 over x looks like this. Or you can just say a positive number on the bottom. What you end up getting on the top, 0. On the bottom, you're approaching 0 from the right. Oh wait, the top, sorry, I'm getting ln, okay, so I messed that up. ln of 0, I'm still getting negative infinity. No one will even know that I made that mistake. And on the bottom, I'm getting 1 over 0 that's really positive, so this is infinity. So I have a negative infinity over infinity, so I'm going to go ahead and apply L'Hopital's rule. Now, L'Hopital's rule says I take the derivative of the top, which is 4 over x, and I take the derivative of the bottom. Now, the derivative of the bottom, I'll write it off here, looks like this. X to the negative 1, and so this is going to be negative x to the negative 2, which is negative 1 over x squared. So this is negative 1 over x squared. We'll continue on another piece of paper here. I'm going to do a copy dot flip, and when I do that, I end up getting 4 over x times a negative x squared over 1, which is going to give me a negative 4x. Okay, so this is what I'm taking the limit of as x approaches 0 from the right. I'm taking the limit of that there. I'll put this in a cloud because I didn't want to write the limit again on that step. I guess I should have. I'm pretty lazy. So now I'm going to go ahead and take that limit, putting 0 in, I end up getting 0. Now, wow, what have we just done? We have just shown, we better have everything in view, that the limit as x approaches 0 from the right of ln y, and we just wrote it down every single step. That gave us 0. Now, 0 is not our final answer. What we have just shown is we have just shown that ln y goes to 0. Okay? Now I'm going to exponentiate both sides. This is not an equation, but I can treat it like an equation. So I'm going to go e to that equals e to that. So what is y going toward as x approaches 0 from the right? It's going to e to the 0. So this is an exponent now. So y goes toward 1. And y, remember, was our original function. Where that's what we're trying to see. We're trying to see where does x to the 4x go to as x approaches 0 from the right. And so, wow, so what does this tell us? This tells us that the limit as x approaches 0 from the right of x to the 4x, this equals 1. And we could just write 1 and put a box around that, but I wanted to kind of stress that that is what we did. So that kind of completes this section. I'm going to do one more problem kind of as a bonus problem, but this takes us up to the 45-minute mark. Let's go ahead and I was thinking maybe I should, maybe I shouldn't. I'll go ahead and do number 14, but for most of you, you can just turn this off and say, okay, we've had the lecture on this. Problem number 14, the limit of 1 plus 1 over x raised to the x as x goes to infinity. If you put in infinity for x, you get 1 over infinity right there, which happens to be 0. So basically inside the parentheses you have 1 raised to the infinity. So we cannot directly do L'Hopital's rule on this. We've got to do some tricky stuff. So what I'm going to do is I'm going to label this expression right here y. So y equals 1 plus 1 over x raised to the x power. Now what I'm going to do is I'm going to ln both sides of this equation. Take the natural log on both sides. So ln y equals the ln of 1 plus 1 over x raised to the x. What I can do now is I can bring this x in front by using the power rule for logarithms, and that's what I'm going to do. So ln y equals x times the ln 1 plus 1 over x. And now the strategy is to take the limit of the ln y instead of just taking the limit of y. The limit of ln y as x goes to infinity is really the limit of this right here. And so that's what I'm going to write. X times the ln 1 plus 1 over x. And what is this giving me? Well, x is going to get replaced with infinity, so that's going to be an infinity times the ln of, so 1 over infinity, that tends to go to 0. So this is ln 1, which is 0. This is infinity times 0. Now infinity times 0, what we're looking for is an infinity over infinity or a 0 over a 0. And just like in a previous problem, when we have something like this, we can do some algebra with this expression to give us what we want. So I'm going to continue with this. This equals. So I'm going to go ahead and take this x and bring it down on the bottom. Now I have to be careful with that. I can't just write ln 1 plus 1 over x divided by x, because then I actually change the expression. But I could be a little tricky. So this is on the top of my fraction, ln 1 plus 1 over x. And on the bottom, so we don't put an x there, but we put a 1 over x. That is actually the same expression. And if you did a copy dot flip, copy the top, which is this thing over 1, dot flip, you would end up getting this. And so let's see what happens as x approaches infinity. Well, the top is going to be the ln of 1 plus 0. So ln of 1 is 0. And on the bottom you have 1 over infinity, which is also 0. I need another piece of paper for this. So this is 0 over 0, in which we can now apply L'Hopital's rule to this expression. Okay, so L'Hopital's rule, there's that little h there. This is the limit as x approaches infinity. Well, the derivative of the top. Well, the derivative of ln of something is 1 over that something. This is the chain rule, and then we take the derivative of the something. Well, the derivative of the stuff inside the parentheses, the derivative of 1 is 0, and the derivative of 1 over x, I'll just kind of do this off to the side. 1 over x is x to the negative 1, and the derivative of that is negative 1 x to the negative 2. So y prime is really negative 1 over x squared. This is a different y than we have in our problem here. This is just in a little cloud. You may have done these enough to see what the derivative is. So the derivative of the 1 plus 1 over x is really negative 1 over x squared. Okay. So L'Hopital's rule says you take the derivative of the top, and then you put that over the derivative of the bottom. Well, this is the derivative of 1 over x, which we just did over here in this cloud. This is negative 1 over x squared. Okay, so I mean, this expression is different from this expression, but the limit's going to be the same, and that's what L'Hopital says. So what do we got here? Well, what we have is this guy is the same as that guy right there. So they can cancel. Now, if you wanted to do a copy dot flip, I mean, that's the long way of doing that, but you would end up just getting this expression here. So let's continue. We have the limit as x approaches infinity of just 1 over 1 plus 1 over x. So on the top you get 1, and on the bottom you get 1 plus 1 over infinity. 1 over infinity tends to go to 0, so this is 1 over 1, which is 1. Okay, so we have an answer, but it is not the answer to the problem that I'm looking for. I'm going to use this notation here. It's not used that much, but I'm going to use it here because I think it's good notation. ln y approaches 1. Of course, when we write that down, this is as x goes to infinity. Okay. So that's what we have. So we're trying to find the limit as x goes to infinity of y, not ln y. So what I'm going to do is I'm going to exponentiate both sides. E to the ln y approaches e to the 1. So I can do that with equations. I can also do that with this. And what we have here is e to the ln y. You can use your properties of logarithms. That thing there goes pop. And that just gives me a y. So y approaches e to the 1. E to the 1 is just e as x approaches infinity. So what have we just shown? We got the answer. The answer is e. The original problem said this: the limit of 1 plus 1 over x raised to the x. this equals E. So the original problem is that right there. This equals E. And there's our result. Our answer is E. This is very significant. Some books will actually use this as a definition of the number E. They'll say, hey, this is E. It is the limit of 1 plus 1 over x raised to the x. The limit as x approaches infinity. They'll say that is the definition of E. This is also good too, because if we wanted to try to figure out what E is, and we didn't have a calculator, or, you know, I mean, we just wanted to kind of get this, we can just put big values of x in there, and that will get us closer and closer to E. And so there's a lot of statistical stuff that we can do that we're not going to do in this class. But just know that there are some books that will define the constant E as this. They'll say, here's the definition. Just like the constant pi is defined with circles, they'll say, you know, the circumference over the diameter, and they'll do that. Oh, well, this is E. E is not as simple. We can't just say, oh, we have some geometric shape, and then, you know, but we have to define it this way. So this concludes the section that we're working on, 4.7. Do your homework. Have a good day. I'll see you in the next video.